So let's have one more term that we can OR. Then here, then the last term that we can have is, let's have A or B or D, right? I don't want something similar to that question because I don't know if it's in the assignment or not. Then here's your not B, it's inverse, right? Okay, so here let's use C or D not. Okay, great stuff. We're ready now. Okay, so from here we can see that this is your AND gate. Remember, this is the AND gate. So this AND gate has got 4 inputs, A, B, C, D, right? A, B, C, D. So it's gonna be a 4-input AND gate. It's so nice that you can just use this AND gate and then make as many inputs as possible in this course. All right, so it makes it easier. And then here you have A, B not, C. So it means we have A, B, this is an AND gate, right? Then, but the B should be inverted. So we need to invert it before we send it to the AND gate. Then we're gonna have an AND gate that will cater for this. That will combine this A, B and the C, right? Okay, so now let's draw it so that you can understand properly. Just wanted to charge the laptop. Okay, it's perfect. So when you draw it, you look at all your inputs, right? Your inputs is A, B, C, D. There is nothing else here. In other cases, your input will be A, B, C. Here it's only 3. I don't see a D. But if there's a D, then you will also need a D, right? So your inputs are going to be, I want you guys to make these conductors. Imagine you're working on a breadboard. So we have these conductors here. This is for your inputs. Then this will be our A. This will be our B, C, and then a D. For the first gate, A, B, C, D, we know it's a 4-input AND gate. So that one is pretty much simple. We're going to take all these inputs, A, we're going to take B, we're going to take C, then we're going to take D. Let's see, did I record this? Yeah, okay, perfect. A, B, C, D. So this is going to be our 4-input AND gate, right? AND gate. So since this is a 4-input AND gate, if, for example, if this was a OR here, an OR, and an OR, right? This was still going to be the same. Then here we're just going to change the gate into an OR gate. Understandable. The OR gate is this one, this gate. So to add all of these inputs, I was basically just going to change the gate, right? Use a different gate for that. Where's my Control Z, Control Z? Where's my undo? My eraser then? Okay, perfect. So it was going to be a 4-input. It's basically a 4-input AND gate. Then we come here. So we have A and B. A and B, this is an AND gate. But you see the B is inverted, right? So we pull our A, we conduct the A, then we conduct the B. The B is inverted, so we need a NOT gate, an inverter here. Now we have A and B not, right? Great stuff. So A and B naught. So now we need a C as well. C, what's going to happen with the C? C mixed with this output. Remember our output here, it's basically this, right? It's basically A. Here's the A. It's basically A, and then it's B naught. This is our output here, B naught, right? We took B and then we just inverted B. So we need that to be ended with a C. So here's a C. C. We conduct a C. Then we end, sorry, it's an AND gate. Then we AND these two together. So we have A naught, B naught, and C. So we have this one, right? So just to answer, okay, just to answer this one a bit. So this is what, so here we have this one, right? So we have A or B or D. So it means it's a 3-input OR gate because of this plus signs, right? So we're going to conduct from A, then B, then D. This is a 3-input OR gate. 3-input OR gate. For an OR gate, I know my drawings are not nice, guys, but here's an OR gate here. So this has an A, it has a B, it has a D. So we have this. So here, again, we need to OR this. We need to create this one as well. Then we're going to OR everything together. So we need to create this one. So this one is C or D naught. So this is pretty much simple. It's a 2-input OR gate. So we need to take C as it is, and then D, we're going to invert it. So we take C, D, we need to invert the D. Into an OR gate. It is C, here's C going, D changes into a D naught, and then after that, we OR them together. So we need to OR everything together. Check this one, or this term, or this term, or, right? So we have a big OR gate that has 4 inputs, and our output is F. Any questions, guys, regarding the logic gates, logic circuits, logic gates? We check in the chats. It's like we multiply sign and addition sign. You know, you can always talk. Eh? It's difficult to read here. Selfie. Selfie. Any questions, guys? regarding the logic gates? Do you understand now, or you need me to make a different example?
You can hear me? Can you hear me now?
Yes, I can hear you now.
Okay. Can we please go back to the yes. So my question is, we are having the inputs A, B, C, D plus A, B naught, and C. So my question is, if we let's say we are having this one, and then the inputs are A, B, C, D in brackets. And then we remove the addition sign. And then we make brackets for A, B, C.
We make brackets for A, B, C, okay?
Yes.
And
then we also have, we also remove the plus for the ABD, and then it remains multiplication sign. And then we leave the addition sign. How are we going to draw the logic gate for that one?
Okay, so this is an AND gate, this is an AND gate. So this will make 3 input AND gates, right? So this will be the AND gate here, right? So the only change is here. So this will be an AND gate. We have this AND gate here. Then this one, let's say this gate is this, right? And this will be this gate here. And then this one will be this gate here. And then this one will be this gate here. So here, this is where our changes start, right? So here,
Yes.
we're going to have, you're going to use 2 gates. So this gate, check. Remember? I get where you're coming from. But it's simple. You must always take it back to maths, right? This is, for example, x, y, z plus x, y, z. Z is the last one. Plus, I don't know what's plus b or plus a. So this is a. So these ones must be together. A, B, C, D. So now these ones, they're going to go into a 3-input AND gate. This will be a 3-input AND gate, right? You have this one, this one, this one into a 3-input AND gate. So the output of that gate will be this, this, this. If it was mathematics, it was going to be X, Y, Z. Now you want to OR it with an A, for example. So now you take this output with this input. So these 3 inputs, now they made one output here into an OR gate. You understand? So the only thing is, instead of using, if it was an AND here, we're going to use one gate, one AND gate. Because there's an OR, we use 2 gates. Are you with me? So we only changed here. We only removed this one, didn't feed it here, right? We didn't feed it here because this sign is an OR, it's a plus. We took it and then we created an OR gate that will combine these ones, all these 3 with this one. Understandable? Are you guys with me? I can't see. Sophie, Sharon is happy, Andre is happy. Olivia is very quiet today. Sophie, did she? Okay, she didn't type anything. Sophie, are you happy? Okay, I think she said she's happy. All right, guys. Next one. Which one do we go to? Karnaugh maps, sigma notation, expanded form, SOP. Which one do we go to? I'm going to sigma notation quickly. Okay, great stuff. Let's go to sigma notation. So remember, this one will always be in this late, what is it, assignments. It will also be in your exam, right? It's always in your exams. So you will get this, definitely. So another one, quick, it's basically just your sigma notation. I just want to remind you guys, I know you know everything by now. So sigma notation is basically a sum of min terms, right? A sum of min terms. When they say sigma notation, they might give you A, B, C, D. This is in SOP form, right? Sum of product. And then they might give you, let's do another AB. We won't do a lot, maybe just 3 times so that we can have time to cover most things here. A, B, C, D. Last one, A, B, C, D. A, B, C, D. Then this one might be not, this one might be not, this one might be not, then everything here might be not. So I said the first thing that you can do to make it simple for yourself is to write this, represent this in a binary form. So if it has no complement, it will be high. If it's complemented, it will be low, high, low, all right? This will be low, high, 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 right? And then everything here will be low, 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 low. Then from there, you just convert this straight into decimal. Then you will have your sigma notation. So remember, I always say this is 2 to the power 0, this bit, and then this one is 2 to the power 1. I know this is a 10 because I'm used to it. 10, 10 is a 10. 10, 11 is an 11. So I just want to show you. So this 2 to the power 0 is always a 1. Everything to the power 0 is always a 1. 1, 2, 4, 8. 1, 2, 4, 8. You don't need to write this, guys. You don't need to write this. That I'm going to remove it after this. I just want to show you where 10, 10 comes from. I know you know it though. Okay, then 0 multiplied by 1. So I say, here I'm saying this bit is not present. So 1 is not present. So here I'm going to get a 0 plus, then 2 is present. Others, they say 1 multiplied by 2 or 2 multiplied by 1. So 2 is present, right? This bit here is a 0. So 0 by 4 is 0. So this one is not present. The light is off here. Then here, the 8 is present, right? And 8 is present. So 8 plus 2 is equals to 10, right? So this is equals to 10. So here, it's basically 1, 2, 4. This one is 7. This one is 7, and this one is 0. So our final answer here will be, let me just delete these things. So our final answer here is going to be 0, 7, 10 in sigma notation. So we're going to have equals to the sum of min terms is equals to 0. Here's our 0, 0, comma, 7, comma, 10. Okay, so we're done with sigma notation. Let's jump to expanded form. Any questions regarding sigma notation? Something close to your assignment, something that you're struggling with? No question. Thank you. I saw someone type sigma notation going once. Okay, while we wait for non-velo. Okay. Let me write the expanded form in the meantime. I loved living in New York. Non-velo, you can also ask, hey? Then it will be quick.
Sorry, sir.
Mm-hmm.
Yes, I have requested. Is it possible if you can also look at the flip-flops?
Okay, the flip-flops, we won't have enough time, but yeah,
Yes.
we'll look at the SR ledge and then the JK.
Okay.
All right, not a problem. Okay, expanded form. So for expanded form, for example, they will give you sorry, I don't know the notation of this. Let's say they give you A, B, C, D. Then they say A, B, D, A, B, C, A, B, C. It's fine. But like this is too simple. Okay, let's do this. A, B, D, and A, B. Not to waste any time. So here what it means is that expanded form, they want you to take this to its original form, right? So you need to look for the variable that's missing here. So if you're going to take ABD, you know what is missing. Let me type it so that we are quick. For ABD, we know we are missing a C, right? C is missing. But now this C, we don't know if it's a C or and not C, right? So we don't know if the C is low or high. Low, high. Then again here, this is for this one. So now we're going to have two terms for this one. We're going to have A, B, C, D, C, D, and then we're going to have A, B, not C, D, right? So we will have A, B, C, D, and again A, B, not C, D. Not C, D. Okay. So now from this, we have our two terms here from this term because C was missing. So 2 to the power 1 is two possibilities. So we have two possibilities for this, right? In its expanded form. So we come to AB. AB, we know 2 is missing. So we're going to have 4 possibilities from this one. So let's do AB this side so that we remain on one screen, right? For AB, we know that B and C are missing, right? B and C are missing. But now what's missing can be CD, right? It can be CD, CD, CD. So what's missing can be CD. It can also be not CD. It can also be C, not D. It can also be not C, not D. So there's 4 possibilities for that. So now in its expanded form, AB is going to result to is equals to AB. The first one is CD. Let me just write it 4 times. AB, CD. Okay. So AB, CD, AB, not CD, AB, not CD, and then AB, C D naught. The last one A B C naught D naught. So all these possibilities are here. Our expanded form. Let me see. What else? Any questions regarding expanded form? Combination is Karnaugh map. Okay, combining the last part of Karnaugh map after drawing. I don't usually attend because it clashes. Karnaugh map. Okay, Karnaugh map. We're gonna look at it now. That's part of Karnaugh map. Okay, not a problem. Not a problem. Okay. Let's look at that one quickly. Let me just introduce what is it? An SR latch. So guys, we had the last class that we had was for the SR latch, right? SR latch. And then I said I also uploaded on my Unisa. Please go check it out. I said there's an SR latch. There's two types. There's an active high and an active low, right? There's one using OR gates. OR gates. This is in my Unisa. I uploaded this and I think it's phase 7 or phase 8. So it normally uses two OR gates. Then this output, this input will be coupled to this output. And then this one will be coupled to this one. Let me just. So now this one is actually called an active high, right? Active high. Active high, right? Active high. So with this one that uses the, sorry guys, it uses the NOR gates. NOR gates. Your R is here. Please guys, don't make these mistakes. Your R is here, your S is here. Then here you will have a Q and then a Q naught, right? And then a Q naught. So this one, we call it an active high SR latch because the normal condition is low. The normal condition is low. So latches is basically it's the building blocks of memory. Why do we say that? It basically just remembers the previous state. It makes its decision based on the previous state, right? So you will see now. I'll just make an example of this one. So now, before you explain this, before you explain it, you need to be able to draw the truth table, right? A, B. So what I uploaded, it has the truth table as well. It has this active, what is it? Active high, the one using the NOR gates and the one using the NAND gate. So now why do I say this? So if you have the normal condition, I said the normal condition is low. So that's why this is called active high. So we'll start from, for example, start from 0, 0, right? 0, 0. So now pretend this is 0. Your input, this is 0, and then this is 0. Okay. So if you feed it a 0 here, you need to know sorry, I always say that you need to know the truth table of an OR gate first. So let's make the truth table of a NOR gate, of a NOR gate. 0, 1, 1, 0, 1, 1, right? So 0, 0, NOR gate. In an OR gate, 0, 0 was gonna be 0, right? 0 and 0 is 0. In a NOR gate, it's an OR gate, then an inverter. So 0 inverted, it's a 1. 0, 1 in an OR gate was going to be 1 inverted, it will be 0. 1, 0 was going to be 1 inverted, it will be 0. 1, 1, it was going to be 1 inverted, it will be 0. So in an OR gate, we know that our output will only be high if both inputs are low, right? So if we have a 0 here, then we have a 0 here, we know that Q is going to be high, right? When Q is high, I know it's a set, for example. Okay, let's see. So if we have 0 here and a 0 here, we know 0 going to 0. Let's say we're taking out 0 here. Sorry, 0, 0, 0, 0, 0, 0. We know here we're going to get the 1, right? 1, because the output is 0 here. So here we're going to get 0, 0. We're going to get the 1, 1 from a NOR gate application. Then we take this one, we bring it here. 0, 1, 0, 1 is taking us back to a 0. So this will be a 0. So let's use green to get the final values. So this is going to be a 0. Then we take this 0 back, 0, 0, 0, 0. We feed it here, 0, 0, 0, 0 gives us a 1. So we know if both R and S are 0, Q becomes 0 and Q naught becomes 1, right? So this will be in the truth table of the SR, and there's no control Z. Oh, there is control Z. Okay, S R Q Q naught, Q naught, right? So we saw 0, 0. So you need to know this truth table. You need to know how to draw this, and you need to know how to draw this truth table, right? And now you must remember this is an rectifier. Sometimes they might say to you, the one using NOR gates, you know it's this one. The one using NAND gates, you know which one is it, right? So we saw that Q is 0. Q, let me just confirm. Q is 0. From here we saw Q is 0, and then here we saw our Q naught is 1. Let's see. Okay, let's see what happens now. So if we have 0 here and then we have 1 here, let's change our S, for example. Let's change our S to 1. If we change our S to 1 here, let me just change the colors and go to blue. If we change it to 1, we know that 0, here we're still gonna get the 0. 0 and a 1. 0 and a 1 gives us a 0. So this will definitely be a 0 now. Then here we're going to take a 0. So we're going to have 0 and 0. 0 and 0 is going to give us a 1. We're going to have a 1 here. If we take this one will be taken. It will come here. Then here we will have 1, 1, 1, 1. So 1, 1 will give us 1, 1 is here. It's going to give us a 0. So 0 here, 0, 0, it will be a 1. This one, we bring it here. 1, 1 gives us a 0. So the final values here, Q is 1 and Q naught is 0, right? So, but for what conditions were those? Our R was 0 and then our S was 1. So our R was 0, 0 for example, and then our R was 0, then our S was 1. Then we got Q to be 1. Then we got our Q naught to be 0, right? Yeah, Q naught to be 0. Okay, so this condition, we call it, for example, this one, we call it a set. So it means it will just set Q, it will make Q be on for this one, right? So let's see from this condition, from this position that we in, So hence we say that it makes the next, it's a building block of the memory. It makes the decision based on the previous state. So now we're going to use this output 1, 0, right? Q, we know it's 1 here, and then this is 0 here. So let's feed the 1 here. If we feed the 1 here, let's use orange now. We take this one, we feed it here. 1, 1. Okay, what do we want to do? So this one was 1, but let's change first. So let's make our R to be 1. The R to be 1. Then our S to be 0. So we want R to be 1 and then our S to be 0, right? R1, 0, and then our output is 1, 0. Q was 1 and Q naught will be 0. So we take this one, 1 and 0. 1 and 0, we know from here, 0, 1, it results in a 0, right? So we're going to have a 0 here. Then we bring the 0 here. 1 and 0. 1 and 0, it's also a 0, right? So this 0, just to double check, if we bring the 0 here, 0 and 0 results in a 1. 1. Then we take this one, we bring it back here. We have 1 and 1. 1 and 1 results in a 0. 0, just to make sure, 0, 0, it results in a 1, right? So 1 and 0, 1 and 0 gives us Q to be 0, Q naught to be 1. So we call this stage reset, right? So here you can see it's just the inverse of this. So this is basically Q becomes a 0, and then Q naught becomes a 1, right? Becomes a 1. Again, now from there we have another one, another stage, which is called, okay, invalid. But before invalid, we need, let's go back to 0, 0. Let's go back to 0, 0. From here, let's go back to 0, 0. Let's set R to be 0 and S to be 0. So if we are here with this output, right, we know that our Q, for example, was 0, 0, and then our Q naught was 1. So we want this condition of 0, 0. I know even in the previous class, I know I put it here, but I was supposed to put it here first. That's why in the previous class, I made a space here, right? So let me go back here, 0, 0. In your book and what they might use, what is it? They will normally just write 0, 0 here and then skip this line. It will show that this is also for 0, 0, right? So for 0, 0, if we have a 0 here, we're going to bring this 0 here. 0, 0 is going to give us a 1. Let's put it here. Then we take this one, we feed it here. Now we have 0, 1, 0, 1, 0, 1, right? 0, 1 is giving us a 0. We take this 0, we bring it here. 0, 0, 0, 0 gives us a 1. So here, 0, 0 will cause Q to be 0, will cause Q to be 0 and Q naught to be 1. Okay, Q will be 0 and Q naught will be 1. But it means this one we have already seen it. So okay, we have this condition already. You see here it is, right? So it means I actually wanted to show you the opposite one. So I was showing you from this memory, right? From 0, 1, from when Q is 0 and when Q naught is 1. But from this memory as well, when Q was 1 and then Q naught was 0 from this memory, right? From this previous state, 1 and 0, 0, 0. Let me show you this one. This is what I wanted to show you. So this one, we will bring it here. We will have 1. 1 and 0. 1 and 0 will give us a 0. I am going to write it here now. It will give us a 0. Then 0 and 0 will give us a 1. I'm gonna write it here. Then this one, if I bring it here, 1 and 0, we know 1 and 0 is basically a 0. Just making sure, bring this 0 here, 0, 0, 0, 0 is a 1. Okay, so we know, you see it's not changing now, the state is final. So Q will be 1, and then Q naught will be 0. So check, this is for 0, 0, but now Q is 1, and then Q naught is 0, right? Q is 1, Q naught is 0. So you need to remember, you need to know this, you need to know that, you need to know how to draw this truth table, basically. So now I'm just explaining how it works. All of them work the same way. Your flip-flops, your SR latch, I don't know if this one is called RS, but I normally just say active high, active low. The one using NOR gates, the one using NAND gates is the same. Okay, now we have this. We have this condition, 1, 2, 3, 4. Then there is a condition that is called invalid, right? The last condition is if you have 1, 1. So we have 1, 2, 3, 4 conditions, which are right. So now what if by any chance you have 1, 1? Remember, guys, this is a set and reset latch. So it means it's impossible. You cannot have both yes and no on at the same time. This basically toggles it. If you've seen a flip-flop or a latch, you will see that it toggles. It can choose. It only chooses one state, right? One state. It's either it's green or red, or it's either it's on or off, right? There's no in between. But you have seen sometimes when there's load shedding or something, that your light becomes on and off. It's like it fluctuates, like you don't know whether it wants to be on or it wants to be off. That we call a race condition. So what is this race condition that I'm gonna tell you guys about? So this race condition is if we have a 1, 1 here. Actually, I need to move very fast now. If we have a 1, 1 here, we have the history of, let's start with the history of 1, 0, with the history of 1, 0, right? So I'm going to take this one, I'm gonna bring it here. So 1, 1, 1, 1 will give us a 0. Let's put it here, give us a 0. So we bring the 0 here. 1, 0 will give us a 0. Let's bring this 0 here again. So we have 0, 0, you see? We have 0, 0. So meaning both of them are off, which is impossible, right? It's impossible. 0, if we bring it back here, 0, 1, right? Remember the output was a 0 here. So now we have 0, 1. 0, 1 gives us a 0. Then we bring this back here. We get another 0. 0, 1, 0, 1, and 0, 1, it's basically a 0. Is still off, you see, basically off. So that is invalid, right? So now let's change, we can't have both offs. Let's change this to, what did we start with? We started with 0, 1, right? 0, 1. So let's change it to 1, 0. 1, 0. Another possibility that we can get here is for Q to be 1, right? You saw here, Q can be 1 and Q naught can be 0. Let's say we come from this state now, 1, 0. So here we feed 1 and 1, 1 and 1, 1 and 1 will give us a 0, a 0 here. We move this 0 here. Let me put it here, this 0. 1 and 0, 1 and 0. 1 and 0 is going to give us a 0 again here. 0 here. Okay. 0 here. 0 and 1. 0 and 1 will give us a 0. So you see our final state is the same. So we're gonna get 0, 0. 0, 0 is invalid. So the whole reason here is that we call this invalid. Invalid. We call where Q is 1, we normally call it a set, right? Set. Where Q is 1, so Q was 1 here. So we'll call this a set. Then we call this a reset. Reset, right? Guys, please go check those things. Let me show you quickly. Whatever you are looking for, it's already there. All of these things are there. Even the previous, our previous sessions that we have, they have been recorded. They are there. All the answers to all of these things are here. Flip-flops, where did I add to? So it's in phase 8, for example. Open SSL. Downloads. I just want to show you that I'm not lying. I know people think I'm lying. Okay. Here it is. So you see all your marks are here. Here's the one using NAND gates. You see, I said the S and the R will be here. Just draw it quickly for you. Here's a clocked SR. So now a clocked SR, it's a flip-flop, ne? Clocked SR, flip-flop. Then you need a JK as well, JK. Here's a JK flip-flop. The only difference is that they have a clock signal, this one. And then you see the building block. This is that active high, the one that we did, right? The active high. It's just that it has this AND gate here. So all of those things are here for the sake of time, but the explanation, the operation is always the same. Operation is the same. I just want to touch the Karnaugh map quickly. So before again, while we're still here, remember this is the active high because you use the NOR gate, right? Then an active low is the one that you will use NAND gates, right? NAND gate. So a flip-flop is basically built from a latch, right? So this is our building blocks for memory circuits. If you want to store any value, if you want to store something, you need to start using flip-flops, latches and flip-flops. So this is an NAND gate, for example, this is an NAND gate. Then you will have your S. I'm just drawing this here to show you this difference between the S and R and the R. So I always made a mistake here in high school between the R and S and the S and R, right? I always made a mistake there. So that's why I'm drawing it for you guys. Q naught, right? Remember this one, we start from 1, 1, right? So we call it active low because the normal operating position is high, right? Okay, I'm going to repeat. I'm going to repeat myself. So this one was an active high because 0, 0 operates. You see 0, 0, 0, 0 operates. You see 0, 0 operates. It's good for us. But 1, 1 is invalid. So when these inputs are high, it's invalid, right? So the normal working conditions are 0, 0, right? So now this one, the normal working conditions are 1, 1, because you will see that when you have 1, 1, everything works. But when you have 0, 0, for example, 0, 0, you are going to get to this state. Where's that state? You are going to get to this invalid state when you have 0, 0. This Q is going to be 1, and then this Q naught is going to be 1 as well, right? So which is impossible. So it means both lights will be on. Okay, and then from there, I showed you the JK flip-flop. Please look at that as well. Just a quick one, just for 5 minutes, Karnaugh maps. Any questions there, guys? Quickly. Let me just see the chat. Okay, so could you do Karnaugh maps again? Karnaugh maps, Karnaugh map. Okay, yeah, Karnaugh maps, I know, guys. Everyone loves Karnaugh maps. Okay, Karnaugh maps, it's a way of simplifying Boolean algebra expressions, right? So let's do it out of my head. So a Karnaugh map, you will always, for this module, not for this module, I know a 3-variable Karnaugh map, but you guys have never done it. You're always doing a 4-variable Karnaugh map. So you will get your X, then you will get all your variables here, A, B, C, D, for example. X, Y, Z. Yeah, let's use X, Y, W, X, Y, Z. W, X, Y, Z. Y, Z. So your Karnaugh map will always be like this. It will always be like this. X, Y, Z. W, W, X, Y, Z. Let's maybe just have 5, right? W, X, Y, Z. W, X, Y, Z. W, X, Y, Z. W, X, Y, Z. Okay, I need you guys to participate now. So here, let's make this one low. Why low here? Let's make this one low, low. Then let's make any recommendation? Any recommendation? Nothing so far. Okay. So let's make everything low. Then we will have everything high as well, right? Okay, so now what do we do? So the first thing, this is similar to the sigma notation, right? The first step that you must do is have the binary representation for this. So the binary representation, if it's complemented, if it's low, this will be a 0, 0, 0, 0. You can OR it with a 1, 1, 1, 1, right? 0, 1, 1, 0, right? 1, 1, 1, 1, right? Then here only by what? We're gonna have a 0 by y. So this is 1, 1, 0, 1, right? Okay. So the next thing that we do, we draw the Karnaugh map. So what is a Karnaugh map? A 4-variable Karnaugh map is just it has 16 cells, right? It's basically this table made out of 16 cells, 4 columns, 4 rows. Why 4 columns, 4 rows? Because we have 4 variables, right? The most important thing after this is the numbering. So again, your lecture can tell you what she likes doing is that she can tell you that make WX to be your column and YZ to be your rows. So you guys can tell me which one do you prefer in this case. But from high school, what we used to do, WX was here and then YZ was here. So WX was our rows and then YZ was the columns. But your lecture, she likes saying that WX must be here. So I don't know which one do you guys want to do. If not, I will choose WX to be here and YZ to be here. But I have seen that she changes now. But in the past, she liked using WX to be the columns. Okay, no recommendation. There's Lebogang. Yes, Charlotte. WZ in the row. WZ. Okay, W. So WX. Sorry, this is YZ. So the first two, right? WX in the rows. Just correct me if I'm wrong. WX. Yeah, this is how we did it in high school. Why is that? So I guess it's right like this. Okay, perfect. All right. So like this, we know that this is 0, 0 WX, but let's number it for you. 0, 0, 0, 1, 1, 1, right? 1, 0. There's confusion, guys, will confuse you. So this is not 1, 0, this is 1, 1, because a Karnaugh map is built like a tennis ball, like a toilet paper roll. 0. There's a mathematical explanation. I forgot it. They told me at first. I totally forgot what the lecture said. But yes, there is an explanation for this. Okay. I was just gramming there. So, okay, 0, 0, 0, 0. So, remember I told you guys about min terms. Min terms, it means for this combination, we will get a logic 1, right? So if we get this combination, our light will be high. Let's say you are designing the alarm system for a Ford Mustang. Then they tell you if all doors are open, let's say open is 0, for example. If all doors are open, switch a light on. So you need that combination. Okay. So if all 4 doors are open, I'm going to put a 1 here. I want this to be on. Then they tell you that if all, maybe this is wipers, for example. If for 4 things, if all seats, for example, are flat, switch a light on. So this is basically what this means, right? So now 1, 1, 1, 1. So you look for your WX. WX must be 1, 1, and then YZ must be 1, 1. So you will have another 1 here, right? And then 0, 1, 1, 0, 0, 1, 1, 0. Sorry, you start with WX. 0, 1, 0, 1, 1, 0, 0, 1, 1, 0. You will have a 1 here. And then here 1, 1, 1, 1. We already have 1, 1, 1, 1. So let's change this to not here and then not here. So this will be a 0, and then this will also be a 0. 1, 1, 0, 0. So this is 1, 1, then 0, 0, right? So let's say this is how you basically plot your Karnaugh map. 1, 2, 3, 4. This is how you plot your Karnaugh map. Guys, there is a, I think in phase 3 or phase 4, right? If you go here, there is a document called Karnaugh map groupings. Karnaugh map groupings. Please, everything is there. All the different groups of Karnaugh maps are there. Here it is, Karnaugh map groupings. I worked it out for you guys. You don't need to think too hard about these things, right? So it's here. Go look for Karnaugh map groupings. I'm just gonna finish. You see, I even show you if it's here at the corner. I show you if it's like this, how do you work it out? I show you if all the ones are here. Do you understand? So all different groups are there. Please go have a look. You will not struggle if you see if you get them there. So let's go back here. So let's make it challenging for ourselves. You guys can tell me as well, where do you want the ones to be, so that we can help the ones who need to simplify. So I want to put a 1 here. I know this 2 can be together, and then this outside 2 can be together. Then let me put 4 here. Can I group this ones, and then maybe we'll just take one last question for a grouping, right? You can tell us how you want it to be grouped. Then we'll do it your way. Okay, so let's say these are all our ones. So when we group, guys, we look for the biggest group. The biggest group can be 8, right? Remember, they can be 1, 1, 1, 1 here, right? So it can be 8. Then the second biggest group, so the biggest group is going to be 8, right? The second biggest group will be 4. Then third biggest 2, then 1. So now in this case, our biggest group is 1, 1, 1, 1, right? So we look for the bigger, for the most number of ones adjacent, right? Adjacent to each other, like ones that are next to each other. So here they are. We know in this group, guys, this group only consists of 1 row, but 4 columns. Check. This group covers this 0, 0, it covers 0, 1, it covers 1, 1, it covers 1, 0. So when we simplify, what do? We look for variables that do not change states, right? Variables that do not change states. So how do we get the variables that do not change states? So we check in this group, what is the value of W? The value of W is 1, and W will always be 1. W will never have another value. It will always be 1. Okay? Why are we saying that? Because this group consists of only one row. And in this row, W is 1. So here's our W. Then X. What's the value of X? X in this group is 1. X will never change its value. X will always be 1 because this group consists of one row. Right? So here's our X. Now let's check Y. So in this group, Y is 0 in the first column. In the second column, Y is 0, which is good, it's not changing state. But in the third group, Y becomes 1. So this is bad. What do? We throw it away. So we don't look at the Y anymore, we go to Z. Z in this group that consists of 4 columns. In the first column, Z is 0. In the second column, Z is 1. So what do? It changes states, so we throw it away. So our values here, our simplified version for this is basically just WX. You guys with me?
Yes, sir.
Okay. Thank you. Then now let's go to the second largest group. The second largest group is these ones that are next to each other. Right? So what do we have? We have the value of W. In this group, we have the value of W being 0, 0, right? This group consists of, let me use the same explanation, strategy. So this group consists of 2 rows. In the first row, W is 0. In the second row, W is 0. So it does not change states, it remains the same, so we take W. But since W is complemented, we need to complement it. So we take not W, right? W with the value 0. Okay, great stuff. Now we jump to X. X, this group consists of 2 rows. In the first row, the value of X is 0. In the second row, the value of X is 1. So what do? We throw it away. Okay, now let's move to Y and Z. The value of Y in this group consists of only one column. In this group, the value of Y is 1. And the value of Y will always remain 1. It will not change at any cost. So we take it because it does not change states. So we take Y as it is. Sorry for the Y. Okay. In this group, the value of Z is 0. So Z is low. So what do? This group consists of only one column, and in this column, Z will always be 0. So we take Z as it is. We take Z, but because it's low, we make it low. So this is basically our answer for simplifying this. Okay, oh, we're not done. We have this one. So we have this naked one here. We need to pair it. So we look for adjacent ones. So remember, I always say this is built like a tennis ball, right? So it means here, this one is actually next to this one. And then this cell is actually next to this one. You know, this cell is here. So this cell is there. So I like drawing this as well, just to show people what I mean. So this, guys, if you turn this around, if you make it the tennis ball, it means this can talk to this one, this can talk to this one, this can talk to this one, this can talk to this one. So that's basically what I'm saying here. This will be able to talk to this one. So we can pair this together. It's the same as this cell just being this side. Then we pair this one and this one. So now we're pairing these two, right? This is our third group. In our third group, this group consists of one row. In this group, the value of W is 0, because it's only one row and the value of W will always be 0. W X in this group, this group consists of only one row. The value of X is 0 and will always be 0 as well. Okay, and then again now, in this group, let's look at the Y and the Z value. What is the value of Y? The value of Y, okay, this group consists of two columns. This column and this column, right? So in the first column, the value of Y is 0. In the second column, the value of Y is 1. So what does it do? It changes states, right? So we throw it away. Then we come back. Because someone didn't correct me somewhere. Okay, let me leave you. I think you saw the mistake. Okay. Then Y, this is 0, 1. We throw it away. Z is 0. And here the value of Z is also 0. So it does not change state in this group. This group has two columns. In the first column, the value of Z is 0. In the second column, the value of Z is 0. So we need Z. But since Z is 0, we need to complement it. Please just correct me quickly. There's something that I forgot. Let's see if anyone can get it. All right, thank you, Andre. Danke, danke. Yes. So W is 0, X is 0, so we need to complement these two, right? So remember it's 0, 0, we complement. Then Z was 0 here and Z was 0 here, so that's why we complemented them. All right, guys. We are done. Any questions? Blizzard. I think you guys are happy now. When are you guys submitting? Thanks, Lebu. Okay, if you guys need anything, please, guys, post. No one types in the comments, in the discussions. Just send something. But I will upload this recording as well. Let me stop recording. But these things are so long that they're irritating. I know you guys don't have